Mm, okay, now I think I'm recording the class. This is gonna be the class for the second group in the afternoon. Please, guys, say hello to the second group. Hello, second group. Good to see the others. Okay, in the previous classes, we were discussing actually the graphical solution of the equations. This is what you saw, remember? So we essentially define, give me new participants because I get some noise. So you get the solution of this polynomial. We discussed what the condition was to actually obtain a solution inside of a neighborhood. If you remember, I said that you have to multiply the function evaluated in the neighborhood range, and then the multiplication of this has to be less than 0. So this will indicate that the neighborhood contain at least one solution. That's what we said in the previous class, if you remember. Okay, so in general, we discussed the graphical solution. We discussed what happened when we have a more complex equation, if you remember. So we actually split the equation in two parts, as in this one. We also make a review of MATLAB, and we review how to do the method in the MATLAB. And also I gave you an example with this plot, and I told you that the solution was about 2.5 something. And finally, I gave you this exercise. One thing, I know that this assignment is not yet in Eminus, right? So it's not in Eminus, but I need to fix something here because I have a lot of grammatical mistakes. I'm gonna try to this was the very beginning of my class, so I have a lot of mistakes, so I need to correct this for you to have a better, a clear, understanding of all the sentences. Give me today to actually fix it. And having some trouble because this was actually written in how you call this? I was in Pages. No, not Pages. What's the other one? Keynote in OS X. So I need to find actually. I need to edit this in the internet. So this is what I need to do, and then you have this exercise. Today we are going to start with the first analytic method to actually solve equations. So we have two types of equations. We're solving algebraic equation and transcendental equations, if you remember. Okay, recalling this. So today we are gonna start. We are in the second unit as well. Remember that the first unit was equal to the error, and then all these definitions and how we evaluate a polynomial using the Horner's method. In the second assignment, sorry, in the second unit, we are going to start with the first method to be able to solve a problem, either transcendental or algebraic, both of them. Okay, so we'll start now considering the equation again, the equation fx equal to 0. Remember, this equation fx equal to 0 could be any equation, but it has to be equal to 0. We also assume that the fx function or equation is continuous on the neighborhood A and B. And also, we recall the definition of the function evaluated in the neighborhood and multiplied themselves are going to be less than 0. So this condition is very important for the bisection method, this condition, okay? In order to find a root of 1, which is this one, lying on the interval AB, which is our neighborhood that we select, we shall determine a very small A0, B0. So when I say very small, it's actually kind of trivial because what's very small? I could say like very small is, -1 to 1. I could say like very small is minus 0.5 to 0.5. So very small means to actually, recur to what we already use. So if you already know the graphical method, if you plot the equations using MATLAB, as you well taught in the previous class, So you will be able to actually give a good approximation of the neighborhood. What I mean is, okay, let's find or let's plot in MATLAB the equations or equation, and then we find a suitable neighborhood so that the bisection method is going to take less iteration to actually be solved, right? So that's the purpose, because we want actually less iterations, because if we have more iteration, so it's going to take more time to solve the method by the bisection method, okay? So we have to determine a very small interval. And this interval has to obey the first assumption when we say that the function evaluated in A0 and B0 and multiply themselves has to be less than 0. And of course, the derivative of this function maintains the same sign in A0 and B0. So the derivative of the function evaluated in A0 and B0 have to maintain what? The same sign as evaluated in the normal equation, okay? So that's very important. This is to guarantee that, or to only obtain one real root of the equation, okay? This is all the assumptions we need now to actually be able to do the bisection method using the neighborhoods, okay? So when we say bisection, I need someone to participate. What's a bisection? ¿Qué es una bisección? ¿Qué entienden por una bisección? Esto es un tema de geometría analítica, digamos, ¿no?
Donde se cruzan, ¿no?
Donde se cruzan, pero un poquito más específico. Bisection.
Cuando una recta se divide en dos partes.
Y esas dos partes, ¿qué condiciones tienen?
Que son iguales.
Exactly. So that's a bisection. So in general, we are bisecting the neighborhood. So we are dividing the neighborhood in halves. Okay. So essentially, if you want to obtain the first value to be evaluated in the function fx, so x1 is going to be a0 plus b0 divided by 2. Right? So essentially, let's actually go to the whiteboard to explain this. So let me load the whiteboard. It's loading right now, so it's going to take some time. Okay, so I'll do my best to actually write something beautiful today. So this is the y, and this is the x. Of course, I'm going to use x, I'm going to use y. So, and we have just this equation, right? So this is my graphical solution. I would say, like, you know, this is, let's just divide this by several. This is 1, 2, 3, 4, and 5. So this is 1 unit, right? So remember, it's a unit. So if you think about this, so the solution is between what? Between 2 and 3, right? So my neighborhood, I would say, like, my neighborhood is actually this. So my neighborhood, I'm going to declare n equal to, this is put like a and b, right? This is my neighborhood. So, and this is going to be equal to, my neighborhood is going to be 2 and 3. So this is going to be my neighborhood. So what I'm doing actually, it's just essentially splitting my ranges. So I'm going to split this here in half. So this is my half, and this is going to be, of course, x1. If you think about it, right? So, and then let's make a zoom here. Let's make a zoom. Let me just try to actually make this like as we do, like, whoop. like this. And let's make a sum here. And then this is 2. Oops, hold on. This is 2. And this is going to be, let's check. Yeah, this is going to be 3 here. So essentially, the half is here. So this is going to be 3. So, yeah. So this is going to be, let me just think, because the half has to be here. So it's in the second half. So 3 is going to be here. So 3. It's kind of difficult to do this in the computer. So take some patience. So this is going to be the half I just computed. So this is the half. Ouch. So, and the half, of course, if you think about it, and I said is equal to x1. ¿Cuánto va a ser esa mitad? Si decimos que es 3 menos 2. No, perdón, ¿cuánto es la función? Es 3 más 2 son 1, entonces sería más o menos 2.5, ¿no? Ahí está. Digamos, ahí está. Esto es la función, ¿no? Right? So, now that we divided the neighborhood in half, we have to double check the condition. So this is going to become actually, oops, 2. 2 is going to be equal to, actually, let's call this A0. And 3. And 3 is going to be equal to B0, right? So this is the ranges. So essentially, so we have to check if my root is here between A0 and X1. Is it the root between X0 and X1? Is the root between A0 and X1? No, it's not here, right? Because A0 to X1 is not, the root is not here. So now the question is the root between X1 and B0? Yes, the root is right here. So now this one, X1, if I just do it again, X1 is gonna become my A1. My A1 and 3, which is this one, or my B0 is going to become my B1. Why? Because now my neighborhood, if you check this, the root it's contained between this range. The root is right here. Right? So now the root is here. So I now, in my second iteration of the method, I'm gonna bisect again this, and then I have to bisect this one. This is my, this is my initial iteration. My initial iteration. This is my, then again, text. Happen here. This is my second iteration. Just call it like my second iteration. Oh, let's call it first. Right, let's call it first. It doesn't matter how I call it. My first iteration. This one. So now I bisected my root here. So I have again to actually ask myself the question, is the root between x2, this is x2, this one is x2. So is my neighborhood between x1 and x2? Is my root between x1 and x2, or a1 and or x2? Is it inside this neighborhood? Yes. Is between x2 and b1? No. The root is between a1 and x2, right? So the root is here, right here. Siempre mi pregunta es, cuando yo lo hice acá arriba, cuando yo lo hice acá arriba, si se dieron cuenta, lo primero que fue es dividir A0 y B0 entre 2. Aquí está mi primera división. Y me hice la pregunta, ¿está entre A0 y X1? ¿Y qué fue? ¿Está? No, no está. Porque esta es mi bisección aquí, no está. Ahora, ¿está entre X1 y B0? Sí está. Entonces ahora mi X1 se convierte en el A1 y mi B0 se convierte en el B1. Y vuelvo a hacer la bisección. Hago la bisección y checo. ¿Está entre A1 y X2 mi sección? Mi raíz. Cierto, aquí está. Pero ahora me pregunto si está entre X2 y B1. ¿Está entre este y este? No, ¿verdad? Entonces, no está aquí. Ahora yo tengo que convertir para mi segunda iteración. Si yo hago, en este caso, ahora hago mi bisección. Voy a dibujarlo otra vez. Entonces, lo dibujo y digo, ¿saben qué? Bueno, hago esto otra vez aquí. Y mi X2 se convierte en mi ¿cuál? En mi A2. Entonces, X2 va a ser igual a A2. Y mi, perdón, este X2 va a ser igual a mi, no va a ser va a ser mi B2. Y en este caso, X1 pasa a ser ¿cuál? A2. Porque estamos hablando en este. Entonces sería X1 o A1, perdón, pasa a ser A2. Es lo mismo, no pasa nada. Y pongo los otros aquí. Entonces, aquí está mi raíz si la vuelvo a bajar, está aquí. Y me voy a mi second iteration. Right? So second iteration right here. So now if you see this, I'm just actually bisecting every iteration. So my bisection here is okay. It's between now I bisect again, sorry. I have to do the bisection. So I bisect here. And then this is going to be my X3 right here. So this is my bisection. It's here. This is equal to X3. So now my question is my root between A2 and X3? Is between A2 and X3? No. Is my root between X3 and B2? Yes. So now again, once again, my X3 is going to become equal to what? To my A3. Right? And then my B2 is going to become equal to my B3. And I can continue this, all the way down to the infinite. But I'm observing something. If you observe this carefully, so now I'm gonna actually do this. It's here. And then the root is going to be here. Then I bisect again right here. It's becoming difficult to do it. So now my bisection here, finally, I'm just going to stop here. This is going to be my X4. And then this is my third, iteration. So again, we can ask the question, where is the neighborhood? And I know that it's between X4 and B3, right? So it's between X4 and B3. And I can continue to do this, and this, and this, you know, all the way down to the infinite. However, if I start actually, you know, minimizing the root, so for the next one, it's gonna be between this neighborhood. So it's gonna be here, here, and then my root is here. So if I do it again, so my root is gonna be here. And then I'm gonna just try to do it here. So, and then this I cannot actually draw in anymore, right? So you see that the neighborhood is actually becoming what? Becoming very, very small, right? And it's gonna be very, 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 very small when actually converges to the solution, okay? This is essentially what the bisection method it's about. So it's just about bisecting several times so that at the end, the bisection is gonna be equal to this. So this is gonna be my solution at the end. So is A0, oops, second iteration, hold on. A0, sorry, AN, just call it AN, is gonna be equal to BN, and then this is gonna be equal to the solution. This is the main purpose of the bisection method.
Professor.
Yes.
Can you repeat the definition?
Definition of what? Sorry.
What you already told about getting smaller.
Ok, vamos a ser tan pequeño que al final el neighborhood o el intervalo AB va a ser igual a la solución. Quiere decir que AN, donde N es las iteraciones, y BN va a ser igual a ¿quién? A la solución. Okay? We're gonna actually see this graphically. Don't worry, we're gonna see it. I just want you to actually get all these things, right? All these done. So, did you get the bisection method? Did you understood what I said? All the iterations process that we have to do to actually get the solution at the end? Did you get it? Did you understand? Any question? No question? Man, I'm a very good professor because you never have questions. Probably I'm very bad that you don't understand anything, right? So,
Profe.
yes.
Ok, entonces entre las iteraciones donde vamos a ir sustituyendo la X1 igual a 1, después A1 igual a X2, ¿no? Y X2 va a ser igual a A2 y así sucesivamente hasta hacer un intervalo muy pequeñito que se acerque a la solución.
Exacto.
Okay.
Sin embargo, tienes que ir seleccionando si tú estás en el intervalo izquierdo o en el intervalo derecho. Entonces tienes que ir mirando eso, siempre. Tienes que ir mirando eso. Esto es gráficamente. Ahorita en un momento vamos a ver cómo se hace numéricamente. Y se van a dar cuenta que esto es uno de los métodos más fáciles. Es como, es muy sencillo. O sea, se van a morir de la risa.
Okay, gracias.
Okay, so let's continue to the class. I'm going to stop actually sharing the whiteboard, and I'm going to move to the presentation. So screen 2, this is the presentation. So essentially, as I told you, we started by dividing the neighborhood in 2. And now fx is going to be equal to 0, then x1 is going to become the root of the equation. Right. So now we have to test it. We have to test it. Sorry, not to taste it. We have to test it, and then we have to check if fx is equal or different than 0. So if fx is equal to x1, sorry, if x1 is equal to 0, so we have the solution. But if fx is not equal to 0, then we have to check numerical. This is numerical. This is not graphical. So we have to check if the evaluation of a0 in f and evaluation of x1 in f and then multiply themselves is less than 0. If this is true, x1 is going to become b1 and a0 is going to become a1. However, if this is not true, you have to taste the other side, the right side of the neighborhood, so that the multiplication of the b0 and x1 evaluated in f is less than 0, so this is going to become true. So in this case, we have to check it, right? If this is true, b0 is going to become a1 and x1 is going to become b1. It's exactly what we did in the previous, in the graphical method. So essentially, if just in case if f1, sorry, a0 times fx1 is less than 0, then the root of the equation lies or is between a0 and x1. Otherwise, logically, the root is between x1 or b0. Once we do that, we have to do exactly the same. So we have to do exactly the same so that if just imagine that you have the neighborhood, it's still the same. You have b1, a1, just convert it, which is the neighborhood if you think about it, and you have to divide it by 2. So you have actually already divided this one by 2, which is the previous exercise. And then you have to compute x2. x2 is going to become a1 plus b1 divided by 2. This is exactly the same what we did in the whiteboard, but mathematically. So now x2 is going to become our root. We have to test it again. If x2 is equal to 0, of course, then x2 is going to become the root of the equation, which is pretty easy to understand. However, if x2 is different than 0, we have to check again the conditions out, right? So we have to check if x2 and f1 multiply or evaluated in the function and then multiply by themselves is less than 0, then the root lies between a1 and x2. And of course, a1 is going to become a2 and x2 is going to become b2. In which case we remained it as this one, as I said. Otherwise, in this case, so a2 and b2 is going to become, or is going to be equivalent to x2, b1, renamed as a2, b2. So it's exactly the same. So and now we do this again. So we're just going to do this again and again and again and again and again. So that if you think about it, this is what we had first, and then a2 minus b2, which is the range of the neighborhood. So now it's going to be equal to the initial neighborhood, but now divided by 4. Right? Si iniciamos aquí, que ese sería el neighborhood inicial, b0 menos a0 dividido entre 2, entonces en el siguiente va a ser b0 menos c0 dividido entre 4. ¿Cierto? And then we proceed to do the same thing, so that xn plus 1 is going to become an plus bn divided by 2. And we have to recheck the root again. So we have to check the n plus 1, the approximation is the root fx equal to 0. If not, we have to redefine the neighborhood so that the root fx equal to 0, of course, is going to lie between an and bn. Essentially, or in summary, we are saying that the bn and a minus an, which is my neighborhood n, is going to be equal to the initial neighborhood multiply 1 by 1 divided by 2 to the power n. So we're going to do this in Excel. Even though this seems actually pretty difficult, it's not. Lo que estamos diciendo aquí es que nuestro neighborhood en la iteración n, right, va a ser igual a mi neighborhood inicial dividido entre 1 sobre 2 veces n a la n, que es el número de iteraciones. Okay? This is actually very equivalent to what we call the limit. Cuando invocamos el límite, les decía que an va a ser igual a bn y esto va a ser igual a la raíz. Si llamamos a la raíz c, c va a ser igual al límite de an igual al límite de bn cuando n tiende a infinito. Quiere decir que el neighborhood se va a hacer tan pequeñito que se va a convertir casi igual a 0. ¿De qué va a depender mi neighborhood? Por supuesto, o mi valor de C o mi precisión de C va a depender de lo que llamamos, ¿qué cosa? The limiting error. Remember the definition of the limiting error? So this is what we just want to do. Okay? So that's exactly what we do. Okay? So we're going to do these examples, of course, but then first I want to show you something in R. So for those that have already R, so I'm going to actually show you how to do how the method works. So you have to pay attention to this area, okay? Because this is the animation that I want to do. Let me just install the animation package because I updated R recently. It's going to take a little time, so just this is fine. Okay, so it's installed. So now, just please turn on your microphone. So now I'm just gonna load the library animation. It's gonna run it. It's run, and pay attention to this side. So in general, this is a package already created in R. So the bisection method fun equal to the function x cubic x plus x minus 1. This is the function. Is going to be evaluated in the range minus 10, 10, and my limiting error or my tolerance is going to be equal to 0.0001. Okay, I'm going to run it. Please pay attention to this one because this is how we are actually dividing the neighborhood. So there you go. So see, half, 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 and of course I cannot see anymore, but this is still running, it's still running, it's still running, it's still running, running, and then it stopped. So the solution is around here, and the precision and the solution is 0.68222. Por favor, coloquen 0.68222 en esta ecuación. Evalúenla, porque ya me cansé de hablar. Entonces les toca a ustedes trabajar un ratillo.
Profe, yo veo muy chiquito en mi pantalla. No alcanzo a ver.
Lo veo muy chiquito, pues ahí no puedo hacerlo más grande, ahora sí te lo debo porque R tiene su...
ya vi la ecuación, ya.
Entonces,
Punto
otra vez
6822, ¿verdad?
Así es, en esta ecuación.
Profe.
Yes.
Me dio menos 2.58 por 10 a la menos 4.
So it's a very small, right? So this is actually less than this. This is the tolerance. So that's how you obtain the solution. Okay, this is actually an algebraic equation, right? Purely algebraic. Now we are going to do it using a transcendental equation, okay? So let's do it again and just pay attention to this side. Don't worry about the function. This is just a tool. So now we have a cosinus of it. So there we go. So now we have a function half, 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 and it becoming very small, very small. So it's still working, still working. And now the solution we got is actually 0.73913671.875. So please substitute 7391 in this equation. Sustituyan este valor hasta el 1 en esta ecuación, por favor. Mientras yo tomo mi Coca-Cola Light para hacer promoción.
Me dio .26.
¿.26? You sure? ¿En radianes?
Me dio menos 0.054 en radianes.
.054. Es mucho, ¿no?
Menos 0.054.
Menos .054.
Okay.
Let me just check again with my calculator. So I'm going to use cosinus of 0.73901 minus 0.7391. Me da .00126. No sé si lleguen a verlo ahí. No creo. No se ve. Pero es me da .00126. Coseno de .7391 menos .7391 me da .0000126. So we respect the tolerance. And of course, if I'm just using actually 5 digits. If I use all these digits, I'm gonna get actually less than this one. So this is one example of how the bisection method works. Of course, this is using R, right? This is using R, this is using this package, animation, but you are not gonna do it with animation package because you have to do it using actually numbers. So this is just for help. You can use this for help. Okay, so in general, we are going to discuss several examples. So these are the examples that we're going to use this. But first of all, I want to tell you that the bisection method, even though some professors discuss the implementation of the computer, I would say like if you actually implement the bisection method in a computer, it means it means you understood.